Hello and welcome to this presentation on DirectX11 TextureMapping. As you probably know by now, texture mapping is the process of taking a texture and mapping it onto a collection of one or more polygons. One of the challenges is to match up the vertex in a polygon to the vertex in the texture map. And the way we do this is to use texture coordinates. Often these coordinates have the letters U and V. So this vertex here might want to map to the upper left in the image, and this one might want to map to the upper right in the image, and this one might want to map to the lower left. The texture coordinates typically range from 0 on the left edge to 1 on the right edge for U, and they range from 0 at the top to 1 at the bottom in V. Notice that the vertical coordinate is inverted from what you may be used to. This is very common in image programming, in image coordinate systems, for the vertical coordinate to be positive down. Normally the range is from 0 to 1, but you can have larger ranges. And if you do, then what would happen is you would have a tiling or wrapping effect where if you went, say, from 0 to 2, you would have 2 copies of that texture within the area that you're mapping it to. So it would wrap or tile that particular texture. Another possibility is to create what we refer to as animated textures. And there's a few different ways of doing that. One is you can just actually load up multiple texture files and just change them. So you can change the texture on an object just by changing the texture file it's rendered with. Another slightly more efficient technique is to use what we refer to as sprite sheets. And with sprite sheets, you essentially have a single texture that has multiple cells, and each cell represents a particular image in the animation. And so you can modify the texture coordinate. In this case, the texture coordinate here, the U texture coordinate at the end of this first cell, would be 1, 2, 3, 4, 5, would be 1.0 divided by 5, so the U would be 0.2 right here. And the V here would be 0.33 because it's a third. There's 3 rows going down. So that's another way of creating animated textures on an object. A final possibility is that you can modify the texture coordinates in a shader, like the vertex shader, and you can get some interesting effects by doing that. DirectX has a capability referred to as texture filtering, and in texture filtering we've seen in the past the problem of, if you zoom in really close to a texture, you can see some pixelization and you see problems of minification and magnification. And so DirectX has a capability of exposing the filtering features on the video cards. And they do this with what DirectX calls a sampler. And so there's a variety of sampler properties that we'll see. One of them includes a texture filter. Another property includes this wrap or tiling mode that we'll take advantage of. In order to do texture mapping, one of the first steps is to actually load a texture from a file into some DirectX object. In this case, it's referred to as a resource. It used to be in DirectX 9 they had a nice function, something like DirectX load image from file. In DirectX 11 they've taken out that nice function, and Microsoft uses what's called a Windows imaging component, and unfortunately there's not an easy function in DirectX to do this. So there's a third-party toolkit called the DirectX Toolkit, which is hosted on GitHub. And this does have a nice library that has a really simple function call for us to load a texture file. So if we go to GitHub, at this particular site, you see the repository for this DirectX toolkit, and you can download the zip file, and when you extract it, one of the top level folders has a name of DirectX TK Master, and in there are a variety of Visual Studio solution files. And so you can choose the appropriate solution file for your version of Visual Studio in your operating system. When you load up this DirectX toolkit, you will see something interesting that you may not have seen in Visual Studio before, and that is a DirectX solution can be made up of one or more projects. So in this case, this DirectX solution is made up of 4 different projects, and one of them is the DirectX toolkit. And this is really the one that we need for now. We may take advantage of the audio part of it later, but for now we're going to use just the DirectX toolkit. And if you right click on it, on this project, you can build or rebuild just that part of it. And if you build that, you will get the output of that is not an executable. It's designed to produce a library file. And so when you do that in the bin folder, there will be a DirectX toolkit library. So there's an include folder that has the header file. There's this longer path within the bin folder that has the library file, and that's what we need in order to access this function that loads a texture for us. So there's a few steps we need to modify in Visual Studio to be able to access this. The first is in our project properties. We need to specify the path to the include folder. And that path is right under that master folder called INC or include, and I believe it's the wick texture loader.h that we want to include. So in our project properties under C++ additional include directories, we add this path. In the linker section, we add the path for the library file, and notice that the path that I use is created a Win32, so if you have a 64-bit project, you'll need to make sure you build a 64-bit version of the library files. So you gotta make sure you have the right target platform for the library file as the project type that you're making. So we include this path to the library file in the linker additional library directory section, and then in the linker input we add an entry for this DirectX toolkit.library file. Once you've done that, then in your code you can add an entry for a resource view texture, and in order to load it you need to include this wick texture loader.h, and in the initialization we can create this wick texture from file. We pass in the Direct3D device, we pass in a Unicode relative path to a typical image file, and what I have done is in the project I've created remember we have a source folder now. I've also created a media folder. You may want to call it images. I'll call it media. And in there I've got a sky texture and I've got this little penguin guy. And so I'm creating two billboards, which are just rectangular poly objects. And on those billboards, I'm going to map a penguin on one and a sky texture on one as a background. In the rendering part, when I go to render one of the billboards, I'm going to, prior to that, I'm going to set the texture as a pixel shader resource. So notice this is PS set shader resources. I'm setting the texture as a pixel shader resource. Before rendering the second billboard, I'm setting another pixel shader resource as the other texture. We need to talk about how to get the texture coordinates in the vertex. So this requires us to change or modify the vertex format that we used in the past. So in the poly object, we now have a vertex that's a vertex list that is a collection of vertex position texture. And if we look at that, it no longer has a color and a normal. We're not going to do lighting in this example, but it has a three-dimensional position and it has a two-dimensional texture coordinate. So if you actually wanted to access each one individually, I guess it would be .x and .y instead of .u and v. So we need a two-dimensional floating point texture coordinate. Along with that change in the vertex format, we also need to change the input layout to match that. So in one of the initialization steps, when we go to create the input layout, we need to modify it. The first one is the same, its position, and it's a three-channel, 32-bit float for X, Y, and Z. The second one is named text coordinate, and it is a two-channel, 32-bit float for X and Y or U and V. So it's important that this vertex description and this input layout match the data that's in your vertex. That change is also reflected in the shader code. Notice that the vertex in struct has a three-dimensional floating point position and a two-dimensional texture coordinate. The vertex out is very similar, except the position is extended to 4 dimensions to allow us to have this homogeneous screen clip space, and the texture coordinate is still the same. So in the vertex shader, it's pretty simple. We just do the multiplication by the constant data that's passed in, which is the worldview projection matrix. So this is what we've seen before. We take the local coordinate system, x, y, z of the vertex, extend it by 1 to 4 dimensions, and multiply it by the worldview projection to get it into homogeneous screen space, and we send that along to the pixel shader. The texture coordinate we don't do anything with, we just pass that along to the pixel shader. An additional step that we need is to set what's referred to as a sampler. So in our application, we also create, in addition to these textures, we create what's referred to as a sampler state. And when we create the sampler state, we define the filter that we want to use, and there's different types of filters that you can use, and some have better performance and some look better, so you can try them out. And then we also specify that we want to use this wrapping mode for the U and V, which will allow us to do the tiling. So this sets the sampler state, which tells DirectX how we want the texture to be sampled. That creates the sampler state, and then when we render, we have to set the sampler state for the pixel shader. So in the shader code, we are setting the sampler, and we are also setting the texture for the pixel shader, and that gets passed into these two global level variables, the shader texture and the sampler, or the sample type that we've created. When those are passed in, then we can, in the pixel shader, it's fairly simple to ask the texture to take a sample at this texture coordinate using this sampler type, using this particular filter and wrap mode. And that gets us a 4D color, RGBA, and that's what gets returned and rendered for us. The last thing that we haven't seen is the actual texture coordinate itself. So in the poly object, when we create the billboard, it is simply a rectangle that is 0 to 1 in X, 0 to 1 in Y, and it lies in the XY plane, so it has a Z value of 0. The texture coordinate is 0, 0 here for vertex 1, because the V value is positive going down, and it's 1, 0 here for vertex 2, and it is 0, 1 for vertex 0, and it is 1, 1 for vertex 3. So you have to remember that the vertical coordinate of the texture, the V or the Y, is actually positive down, and that's a common mistake that we want to try to avoid. When we get all this right and run this, we see a scene with the penguin mapped onto a billboard and the sky mapped onto a larger billboard. And if we back up and look at this in wireframe mode, you can see that it's just two polygons making up that rectangle that are scaled to whatever size we want. And just to give you an example of tiling, if we were to change the horizontal texture coordinate to range from 0 to 1 to 0 to 2, then it will be tiled or doubled in the horizontal direction. So now you can see that the penguin is duplicated in the horizontal direction. It's tiled, and you can tile in the horizontal direction, you can tile in the vertical direction, you can tile in both directions. The sky texture is also tiled, and unfortunately there's this not very attractive seam because this particular texture hasn't been made to support tiling, and there's a technique that you can use to get the seams, get the left and right edge of a texture to match up so that seam isn't very obvious, and get the top and bottom edge to match up to reduce those seams, and they look a lot better when those textures are created so that they are tileable. So this concludes this presentation on DirectX 11 texture mapping, and let me know if you have any questions.